Okay. Okay. Yeah, I'll talk a little bit about an article that every one of you uses. Everybody has a hands-on experience with that, even if you don't know it. I'll talk about how we use catalysis in purification of automotive exhaust gases, and it's a very interesting area, very challenging, and our product is just clean air. This prepared with the help of my co-workers from BSF, formerly Engelhardt. I want to start also with a little bit of history. Some of you are probably were born later than the 5 Series was introduced. But when the 5 Series BMW introduced, that was before the regulations kicked in. And that car, in 3 days, emitted the same amount of CO as today's car emits in 3 days. I mean, in a whole year. So we are talking about 2 orders of magnitude difference in the emissions from automobiles. It did not come because automotive companies were very altruistic. It came because there were regulations. And the regulations were changing, and I don't have the pre-1972, but just look at the past 15 years. We go from, for the NOx control, we go an order of magnitude down. For hydrocarbons, we go to an order of magnitude lower than 15 years ago. And in addition to that, in addition to the fact that the regulations are becoming tighter, of course there is a pressure of precious metals pricing. Just, I like examples that give you a feeling of the magnitude. For example, if you're talking about the PZEV, the partial zero emission vehicle regulations in California and hydrocarbons, that's 10 milligrams per mile. That means that if you fuel your vehicle and you have a couple of drops that fell on the ground, you already blew your regulation. So on one hand, it's a very tough business to be in, and of about 200 catalyst companies in the world that make chemical catalysts, there's less than half a dozen that is capable of supplying catalysts for automotive industry. It's a tough business, and I'll talk about the challenges. But on the other hand, it's great to be in a business driven by regulations. I'll talk a little bit about what exactly is the catalytic converter. And of course, we have a communications department, so I have to use some of the wonderful graphics that they create. You have a car, you have a can, and in the can, there is a monolith. And monolith, of course, has, I guess I'm talking faster than it goes. There's a monolith, ceramic honeycomb, sometimes it can be metallic. It's high geometric area. The gas from the engine comes through this. It can be either close to the engine, then it's close coupled, or it can be on the floor. And the honeycomb is covered by what is called the wash coat, which is primarily the support for precious metals and also oxygen storage component. And the chemistry is pretty simple. Basically, we're looking at hydrocarbons, NOx, and CO. And we're converting CO to CO2. We are reducing NOx to nitrogen. And I'm faster. And we're burning hydrocarbons. That's very simple. How much more simple can it be, right? But as we all know, devil is always in the details. And let's look at this. I'll make a statement which may be a little exaggerated, but it's pretty close to reality. Automotive catalyst deals with one of the world's most challenging chemical systems, and it is the most complex part of a car, though it does not have any moving parts. And that's why I think some of the statements will clarify that. When you get into your car and you turn your key, irrespectively of whether it's in the garage or in your driveway, it's at ambient temperature. And the catalyst basically has to start working almost instantaneously. I'll show you a graph where it shows how quickly you exceed the limit if you don't have a catalyst. And very few people understand that if you are going on the New Jersey Turnpike or anywhere else in a heavy car, fully loaded at full speed, which most people probably go a little higher than 65, The catalytic, the converter and the manifold, the exhaust manifold, are glowing orange hot, and I'll show you a picture of that. You just don't see it because the cars are well designed and you don't feel it as well. It has to transform several compounds. We've seen that both oxidation and reduction has to happen simultaneously. They are initially present at very low concentrations, and they are varying depending on where your foot on the gas pedal is. When you push the gas pedal, the space velocity changes by an order of magnitude, and so does the concentration. So sometimes the catalyst has to deal with realistic change of 2 orders of magnitude. We have to convert them with 100% conversion, very high selectivity. You cannot fine-tune, you cannot regenerate, you cannot do anything with the catalyst. As a catalyst manufacturer, I have to guarantee that this catalyst lasts through the useful cycle of a vehicle. And useful cycle is actually determined by regulations. And if we're looking at again, the ones that I mentioned for California, that's 150,000 miles. That means that the catalyst has to be guaranteed to meet regulations at 150,000 mile exposure. And when we're talking about heavy-duty trucks, it's 400,000 miles. But 400,000 miles is a requirement of a regulation. The OEM requires 1 million. So now imagine a catalyst that sits in a real inferno and still has to last 1 million miles. One very important thing, its operation has to be detectable by onboard diagnostics. Have any of you ever had a chance when the MIL came on, or otherwise known as check engine light? That basically happens only if the catalyst stops working or if the oxygen sensor stops working. So MIL is primarily about the emission system. How do we check that? That's also a very interesting story. How do you detect that? So talk about that a little bit. And it has to be cost efficient. I'll talk about the cost also a little later, but just one question. Has anyone ever bought a car because it had a great converter on it? Okay. The ultimate measure of performance is the transit test. Basically, when we're talking about meeting regulations, they have to be met when the car is running what they call the Federal Test Protocol in the United States. What we do is we put a car on what is called a chassis roll. There's a big 48-inch roller. The car is secured. We put a fan to simulate road driving conditions. We put either a person or a robot driver, and we run a cycle. An FTP cycle lasts about 13 minutes. That's what it looks like. This is just the speed graph. You start, then you accelerate to about 20 miles an hour, then you slow down, then you accelerate again. This is the first hill. Then you stop, and no, that's just city driving. You stop, the red light changes, then you go, and maybe it's a faster acceleration to about 55, and then we go simulate stop and go traffic, and then there's the second part of it, the second repetition of the first acceleration, and then recently there was a high-speed portion added, which goes up to 80 miles an hour. So basically what we're seeing here is that you cannot just take any static characteristic of a catalyst and say it works. You cannot even screen them by static characteristics anymore. The ultimate test is always transient. And we collect second-by-second data, and you can imagine we have about 40 channels that we collect data on, and they're second-by-second data. We also collect the gas into bags. There's bag 1, bag 2, and bag 3. This is cumulative amount. And that's how we certify the vehicles for the regulations. What are these transients? How are they, if we translate that to something that the chemists would understand? We have heat up rate of 300 degrees per minute. If you think about it, and if you're running lab units, you probably go at 10 degrees per minute, maybe 5 degrees per minute. I have to have lab units if I hope to capture this. I have to have a temperature rise of about 30 degrees per second to match the vehicle. Even after it warms up, those stop and goes and the sharp accelerations, decelerations give about 100 degrees per minute change in and the temperature of the catalyst. By the way, my catalyst is never uniform in temperature. It always heats up from the front. So that's another story that complicates things. There's constant change between reducing and oxidizing conditions depending on which part of the cycle you're driving. And also, it is experiencing what is called a perturbated flow. And I'll talk a little bit about perturbated flow because without that, catalyst cannot work. If we talk about very simplified way to look at the conversion of hydrocarbons, CO and NOx, and plot that against the air-fuel ratio, basically 14.5, 14.6 is the stoichiometry. If you go below that, the mixture would be too rich, deficient in oxygen, and a lean mixture, of course, is in excess of oxygen. So in rich mixtures, it is easy to convert NOx. So in the rich mixtures, when you have excessive hydrocarbons present, you can reach very high conversions. But then as soon as you go into deficiency of reducing agent, your conversion of NOx drops. And well, the reverse is true for oxidation reactions. So we need to figure a way how to operate the engine at the crossover point where everything is really relatively high in conversion. And the stoichiometry usually referred to as lambda 1 stoichiometry. And if you are over lambda 1, that becomes lean condition. So the problem is solved pretty much like it is solved at home with a thermostat. The thermostat heats up and cools down your temperature in the house in a little bit of something that looks like a wave or a sinusoid, right? That's the same thing that happens in the car. The car runs a little bit rich, a little bit lean all the time, alternates. The frequency is about 1 hertz. And why do we do that? Because we need to have oxygen for oxidation, and also we need to have reducing atmosphere at some point for reduction. And this chemistry is basically happening because we have something that is called the oxygen storage component, or you can call it an O2 buffer. And in general, we're trying to stick to lambda 1, but it's only going to be time averaged lambda 1. So what is the OSC, the oxygen storage component? Everywhere you look at every catalyst ever made for three-way catalysis for gasoline vehicles, cerium oxide is the basis of the oxygen storage component. It has, this is very simple. This is almost like, chemistry 101, but I'll repeat it so, we know what we're talking about. We have cerium 4, cerium 3, and when we have the lean cycle, then it goes to cerium O2, and during the rich half cycle, then we have oxidation of CO and hydrocarbons affected pretty much by the oxygen storage compound, the oxidized form of cerium. And that's what allows us, while this is happening, we at the same time can have reduction of NOx happening, and also in the lean part of the cycle, you can take NOx, and it also can work as an oxidation. So basically, having cerium allows you to have both oxidation and reduction in time average and increased conversion, and allow car manufacturers some room as far as where they want their lambda to be. The heart of the catalysis on the OSC is kind of a part of stoichiometry of the catalyst, but the part of catalysis is basically affected by precious group metals or platinum group metals. These are primarily palladium, rhodium, and platinum. And in a very simplified way, we can say that platinum has very good oxidation activity, very good for oxidizing of CO. Palladium has excellent hydrocarbon conversion, and rhodium is very, very important for NOx. But that said, that's simplifying, that's taking it to too high of a level to be true. But a couple of things that I wanted to talk about here. The design of the catalyst itself is very tough because, well, this is all good and dandy, but when you have platinum together with palladium, it alloys and then it loses its activity. You can have alloying of rhodium and palladium. That also makes catalyst less effective. Rhodium likes to be on a good support because rhodium is the most expensive metal. I'll talk about the impact of the price of rhodium. Anyone who is dealing with rhodium, especially on the carbonylation side, probably still remembers how painful it can be. But in general, if you put rhodium on a good surface where you hope to keep its dispersion high, then those surfaces usually are active towards rhodium, and so there's many problems with that. Therefore, we're trying to segregate them. In a lot of cases, if you look at our catalysts, you will see that the wash coats, there's maybe 2, sometimes 3, and there are cases where there are even 4 wash coats because of different considerations why we need to segregate them. But the primary driver, meeting regulations for us is not a big deal. Meeting with the lowest amount of precious metal, that's when it's becoming interesting. Now imagine that you are a car company and you are in 2004 designing a car with a catalyst, and you plan on having 200 milligrams of rhodium in that car. At about $500 per troy ounce at that time, you're planning less than $5 on a car of rhodium. Now the car takes a while to design, and when it goes into production, we're looking at maybe 3 years now, and it's maybe 2007. And the price of rhodium is now $5,400 per troy ounce, and that's dollars. And that means that instead of $5, now you will have about $50 of rhodium. And if you are looking at the peak here in June of 2008, you're looking at maybe 60 or 70. And every dollar on the price of a car is very important. Now imagine that compared to the design, your price went up $50 per car, and you have a platform that makes 2 million vehicles a year. Adds up. So if I as a catalyst designer, if I can take that 200 milligrams down to 190, I take 10 milligrams out. On the scale of US market, that's $50 million. On the scale of world market, it's $150 million. 10 milligrams of rhodium per catalyst is $150 million of worldwide impact. So of course, this is our biggest pressure, to reduce the amount of precious metal in the catalyst. Again, just reiteration, this is how the monolith would look like if you were to take a micrograph. You would see that there is a cordierite walls, and then there is a catalyst here. And the catalyst normally is layered, as I said, in series, alumina, promoter stabilizers, and segregation. I guess it was just redundant. Interesting how, this is the FTP cycle, and this is how the game is played. And this is for hydrocarbons. I'm talking the PZEV limit, 10 milligrams per mile. And the game is basically, this is the heat up of the cycle. This is where the temperature goes up. And if you didn't have a catalyst, in less than 7 seconds, the PZEV limit would be exceeded out of a 2,000 second cycle. So you have to make sure that your catalyst starts working in the first 7 seconds of the cycle. And that also means that you lose or win the game in the first 7 seconds. Here's an example of 2 catalysts. One lit off at about 12 or 13 seconds, and after that, conversion is 100%. There's basically nothing is happening, right? It's just like here. Maybe on the hill here, there's a little bit of a breakthrough. But the game is won or lost in the first 7 seconds of the cycle. Very tough, very tough. And again, I can go from here to here by overloading it with the precious metal, but I cannot do it because of the price consideration. So we play other games. And again, going back to a little bit about what is really important. It's not really the activity. Activity we can achieve. We can make catalysts that, when fresh, you will see nothing coming out of a tailpipe except CO2 and water. It's aging. I told you that I would show you what it looks like. This is a photograph of my engine lab. This is just an aging of a catalyst, a standard cycle. that just sits there and glows orange hot. The catalyst temperature, the catalyst bed temperature for our European aging cycles is 1050 degrees C. And that's when all the materials that we use, they basically stop having surface area. They just start collapsing. And when you're looking at 1050 versus 1075, that's a world of difference. 1030 is a breather compared to 1050. So what happens when the catalyst ages? Well, rhodium will interact with the support. The best support is aluminum for rhodium, but it'll form rhodate. And then this eventually gets lost. Studying these things are very, very difficult, because if you think about the concentrations, if you want to have a fundamental study of the catalyst, and you want to see what happens to it when it's trash versus when it's aged, but I only have 50 ppm of rhodium on support. Do you know of any methods that can give me any clear picture of what form rhodium is in? Well, we actually have found one method that actually allows us to go down to 10 ppm of rhodium and support it. We still can figure out what it does. But that's where the difficulty, that's where the advancement is important. And well, in sintering, that's fresh catalyst. I think it was palladium on DOC, and then look at the boulders of that. Basically, the catalyst loses 90% of its surface area upon aging, and other mechanisms involved in insulating layers and so on. So, with that, we talked about diesel, and I think I have a few more minutes. I'll talk a little bit very quickly about diesel.